Hello everyone. Today I'm going to introduce the paper named Changing the Equation on Scientific Data Visualization. The authors are Peter Fox and James Handler. In assignment 3, we used interactive visualization to show our result of first two assignments. Data visualization is a graphical representation of information and data. Today, the visualization has become a bottleneck. As the ability of data collection increases, data generation cost is decreasing at an incredible rate. However, the visualization cost is falling much more slowly. The main role of visualization is the end product of scientific analysis rather than an exploration tool. However, new database technologies and promising web-based visualization approaches reduce the cost of visualization generation, allowing it to become a central piece of scientific process. Next, I'm going to talk about how visualization can be used from presentation to exploration. In the computing science, visualization has been in the hands of two communities. The first one is human-computer interaction community. They consider visualization as an important technology to study in its own right. Many of tools used by scientists were developed by HCI practitioners. The second one is graphics community, which has often focused on the hardware for creating high-quality visualization in science and other communities. With data visualization on the web, we can do more sophisticated and interactive visualization. At the same time, with Open API, the visualization is becoming easier to generate. Additionally, owing to web-based linking technologies, the visualization changes as the data changes, which greatly reduce the effort to keep the visualization timely and up-to-date. This low-end visualization are often used in business analytics, open government data system, and media infographics, but they have generally not been used in scientific process. Many visualization tools that are available to scientists do not allow live linking as to these web-based tools. Once the visualization is created, it's no longer tied to the data, so that it becomes an immutable information product, which means the data changes, the visualization is no longer up to date. There are many reasons why this is the case, but two of them really dominate the situation. The first is that collecting scientific data is often difficult and instrument specific. As a result, most scientific data is created in a form and organization that facilitates its generation rather than focusing on its eventual use. The second is scale of scientific data. The data scaling problem is exacerbated by the difficulty in linking data from multiple instruments or sources together. Both speed and precision of data retrieval have often been dependent on the quality of the data model. And modeling integrated data from many sources is generally harder than modeling from any single source. With the increase of volume and variety of data, new approaches have emerged, such as NoSQL, big data, and scalable linked data. These approaches let visualization be integrated into analytics process and come with two key capabilities. First, easy-to-use low-end tools will allow scientists to rapidly generate visualization to explore hypotheses. Second, scalable tools for creating high-end visualization are tied to new approaches in data collection and archiving, making it possible to develop and maintain existing visualization at lower cost. However, these tools also create a number of research challenges. First, new approaches are needed for determining how best to visualize particular kinds of scientific data. A strong start in this direction can be seen in the periodic table of visualization methods. It shows a number of visualization techniques organized by the type of data. The second challenge is to create and maintain data and information provenance for visualization. This is also the key to understanding and fixing data errors. The figure on this slide shows Earth observation results from two satellites. The displayed data quality is clearly different from that elsewhere in the diagram. Understanding the cause of this error requires knowing which observations came from which satellite, and even how a day is defined for the data products. But more importantly, knowing when a combination of these factors leads to the aircraft displayed. Another challenge follows from the desirable features that these visualizations are linked to the underlying data and can change dynamically as the data changes, and that this visualization can be interactive in a web context. The fourth challenge is the need to ensure that fitness for purpose is well explained in system that can generate a wide variety of visual analysis products. There are major efforts underway to meet this set of challenges, but research efforts are still required for a scalable and well-enabled solution. Finally, once this visualization product becomes routine, their management becomes a critical part of scientific process. It means we must develop techniques that can maintain the visualization products throughout their life cycle. It is necessary to feature of scientific problem solving that we can find means to open these visualization pipelines to provide suitable data provenance. So what can be done to face these challenges? First, we must work with tool designer to make sure that visualization are shareable during the entire lifespan of scientific process. As one example of this, there are a number of standards for the both graphics and the metadata involved in sharing visualization, but very few of these are supported in current scientific application tools. Second, there has been little work in standardization of workflow and linking technology needed for high-end scientific visualization. Research scientists need to work more closely with their computing colleagues to make sure that these needs are met, and that the development of new analytic methods tied to scientific analysis. Finally, we must work together to explore new ways of scaling easy-to-generate visualization to the data-intensive needs of current scientific pursuits. Then we will evaluate this paper. This paper is well structured, so we can easily understand what each part of the paper is talking about, and also can clearly know the connection between each part. There are also interesting examples like the period table of visualization methods. However, this paper is too short. It's just 2 pages long, and there are few examples in what can be done part. Also, the paper was written in 2010, so the paper is not up to date. Some problems have been solved. That's all. Thank you for your listening.